Welcome back to the second example of our multi-objective optimization module. Here we look into preference-based multi-objective optimization. We use the same example file, the enclosing circle underline multi-objective, and as you can see, we start from the end of the last exercise where we used the second objective to visualize the second fitness landscape. I explained to you that here we have non-conflicting objectives shown by the landscapes. Now what we do is we invert the second objective. We do this by adding the expression where we divide the values, or we use the formula 1 divided by x, and x is our fitness value. And here usually we add a value like 1 to avoid a division by 0, just in case if our fitness value is 0, which would be if the distance of our center point would be 0 to the distance of the middle point of the point cloud. Okay, and then we multiply it by 10 just to have a similar height in 3D as the other landscape. But that's not important. Important is 1 divided by the fitness value inverts the function. So that's the same as inverting from the function to have a minimization instead of a maximization, or the other way around. So if I put in this value, you see the landscape is inverted, so the best values are now at the edge of our fitness landscape. And now the two landscapes clearly contradict to each other. You can look at it in 3D. So here you see where we have this peak, we have the valley, the bottom of the valley in the other landscape. Looking into it in terms of the overlapped value landscapes, we can just put them above each other. So here you see clearly that the two surfaces have not, they don't share the same areas for the optimal solution. So here we just have different visualizations for our fitness landscapes, and to make clear that they contradict to each other. Okay, so after being clear with this, we can now look into our optimization. And in this example, we use the preference-based optimization method for a multi-objective problem. Here you see the Galapagos optimizer. Here what we do, here we normalize all the objective values that we want to put together into a weighted sum function, or into a function to compute the weighted sum for all the objectives. It looks a little bit different than the normalization above, where we have had a list. Here we only get one value from the optimization in the Galapagos version, and we need to define the minimum and maximum values by our own in the script. And in the script we only see the normalization of one value. It's the same formula, but we don't have a list. We only have one value. And here the first difficulty is that we need to define the minimum and the maximum value. So the maximum value for our area is what is shown here. So we assume we have the center point at the corner of the landscape, so somewhere here. These are the maximum values, and then the circle would be in the worst case as big as the radius would be the diagonal of this square or the rectangle that we used. So here we compute the area of this maximum possible minimal bounding rectangle. In this case it would be the maximum bounding rectangle. And the minimum value we just assume would be 0, but of course that's also not completely true. We could also have a better value here, just by taking the center point of the rectangle. And we do the same thing for the values for this area, normalize them, and then here you see the weighting. Here we take these normalized values, they are all between 0 and 1. This allows us to have a better control for putting both values together, because if you imagine if you would have different ranges of values, one maybe between 1 and 1000 and the other maybe between 0 and 1, then adding the second to the first criteria, the first one would clearly overrule the second one, and the second one wouldn't have any effect. So we need to be sure that we put the two objective values in the same range, that we can compare them, that we can weight them against each other, that it makes sense. But you may have realized that the normalization is not always that easy, because often you don't know what's the minimum and maximum value of the function, and therefore you may not be very sure to really have the same scaling. So already here there may be a weighting included in the normalization, just because you don't know the min and max values. Afterwards, here we have these weighting factors. Here we used 3 for the objective 1, the minimum bounding rectangle, and we used the rating 1 for the aspect that the center point should be as close to the edge of our area of the point cloud, or to be as far away from the center of the point cloud as possible. Putting this together gives us a weighted sum. In this case it's above 1, because here we multiplied by 3 and here we have another value. And now here you see this weighted sum value is used as the fitness value for our Galapagos optimizer. And the design or decision variables are the x and y coordinate of the center point of the circle. Now if we run the optimization again, as you are already used, we see here in the background it runs the first generation, tests all the values, and we get a first result. Here the minimum value 1.33, here it's a little bit better, 1.32, but we're not interested in watching it for a while. We are more interested in seeing the where is it? Here, the preview of the created rectangle, circle. Here you see that's now a compromise based on the weighting. Just disable this preview. That's now our compromise solution on our trade-off curve on the Pareto front that corresponds to the weighting of these two factors of the two objective functions. It's clear that if I change the weighting, so let's reduce this to 1, that both are equally important, and if I run the optimization again, our compromise solution will be a bigger circle, because it will move more toward this objective, so the compromise will be closer to being as far away from the center of the point cloud as possible. So the fitness values itself, they don't have a meaning because these ratings, they are relatively arbitrary. Okay, but you see the result is a bigger circle. And of course, if we increase this rating to 100, so to 10, here it's limited, and this to 1, then we will be very close to the optimal for the 1, or the extreme for the 1 objective. So we will come closer to our minimum bounding rectangle as we have found it for objective 1 in the first example, or in the original example where we only used one objective. Excuse me. Okay, here you see we run it for a while, but stop it again. You see here 144, that's the value we found in this optimization, and if you reduce this to 0, you would deactivate this objective completely, and now we will get the 133. At least this was the solution for the first point cloud. Let's see what's the value now. So now we have a single optimization problem again if this rating is 0. Pause it and just show the solution, which is now here our enclosing circle. Okay, so that's the preference-based weighting method that we've seen here, where we can combine different objective functions by weightings for each objective, compute the sum, and use the sum for a single optimization algorithm. You can explore the possibilities here and also look into the normalization difficulties that I've explained and play around with the weightings and try to understand where you are in the search space, in the design space, and where you are in the objective space, that you get an idea of these concepts. In the next exercise, we will look into the optimization with Octopus, but before I will continue with a theory lesson.